All right, welcome back. Section 2.6. We're going to talk about the derivatives of inverse trig functions. If you talk about your inverse trig functions, those are our arc. So like arc sine of x, arc cosine of x, arc tangent, arc secant, arc cosecant. We can also see those as sine inverse of x. Sometimes we see it that way. Generally, we see it as arc sines and arc cosines, so we don't kind of get confused with that notation, with that -1. So our goal today is to be able to determine the derivative of an inverse trig function. But I start with, how do we find the derivative of y equals the arc sine of x? So how would we go about doing that if we didn't know what the general rule was? So what I would do, would be go ahead and get rid of this arc sine. We know if we take the arc sine of x here, we can undo the arc sine, take the inverse of that, which is going to be the sine of both sides. So I could write this as a sine of y equals, now I'm going to go ahead and write it as the sine of the arc sine of x. And the sine of the arc sine of x, they are inverses of each other, so we're going to get just x out of it. So now I got the sine of y equal to x. That's something that we could find the derivative of using our implicit differentiation. Implicit differentiation is a very good tool to be able to use on a lot of different derivatives without having to remember the general rules for them. So if I want to find the derivative of the sine of y implicitly, derivative of sine would be cosine. My angle stays the same. And I take the derivative of the angle. Derivative of y would be dy dx. Derivative of x is 1. So I've got dy dx then as being 1 over the cosine of y. Not necessarily the most useful of things, because we're really interested in that x value, or the x variable. So can we get this cosine of y in terms of x? And from pre-calculus, we sure can. We can go ahead and draw in our triangle. We know that the sine of y equals x. We also know that the sine of y is going to be the angle, so we can let either of these angles be y. We also know that the sine of an angle is equal to the opposite side over the hypotenuse. In this case, we have x over 1, so the opposite side is going to be x, and the hypotenuse is going to be 1. If I think about the cosine of y is talking about the adjacent over the hypotenuse. So I'm going to need this angle, or this side length here. Well, how can I find that side length knowing my hypotenuse is 1 and my other leg is x? So we know that a squared plus b squared is going to equal c squared, where a and b are two side lengths and c is the hypotenuse. So we can go ahead and let this be our a side, our b side be what we're looking for, and then our c squared is going to be our hypotenuse squared, which is 1. So b squared is going to equal 1 minus x squared. So b is going to equal the square root of 1 minus x squared. So I know the cosine of y is going to be the adjacent side, which is, we just found, 1 minus x squared, divided by the hypotenuse, which is 1. So in terms of x, our derivative is going to be 1 over the square root of 1 minus x squared. That's going to be very helpful for us as we get into what the actual rules are, so we don't have to necessarily do all of this work if you remember the rules. And those rules, ta-da, here they are. So here's your critical information for the day. The derivative of the arc sine of u is u prime over the square root of 1 minus u squared. That should look very familiar to us. Notice anything familiar there? The derivative of the arc sine of x was 1 over the square root of 1 minus x squared. So if we look here, we replace that u with x. The derivative of the angle, which was the derivative of x, would have been 1, divided by 1 minus the angle, which was our x squared. So in general, for any function, for any angle, the derivative in terms of x, where u is going to be equal to f of x, we've used that notation before. So where the arc sine of an angle, where this is a function, we take the derivative of the angle divided by the square root of 1 minus the angle squared. arc cosine is the negative u prime over 1 minus u squared, again where u is a function of x. The arc tangent of u is going to be u prime over 1 plus u squared. The arc cotangent is negative u over 1 plus u squared. The arc secant of u is u prime over the absolute value of u, square root of u squared minus 1. And the arc cosecant is negative u prime over the absolute value of u, square root of u squared minus 1. Some similarities you should see. The arc sine and arc cosine, very similar to each other. Arc tangent and cotangent are very similar to each other. And arc secant and arc cosecant are very similar to each other. Arc cos C's, C's, and C's are all negative. We've seen that before when we were working with our derivative. Ding, 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 ding. All right. One of the things that you should see, I've got the arc tangent a little larger. So if we're studying for the AP exam, this one is normally going to be used. It's normally the one that they like to use in the years past. Arc sine and arc cosine, they're a little smaller than the arc tangent, so these two would appear the next most often, and then these other three generally not used. The derivative of your inverse trig functions, you might get a question on the AP exam. I'm not going to spend a miserable amount of time on it. You either remember it or you don't. Hopefully, though, there's that word hopeful again, isn't it? I'm very hopeful. If you forget what the derivatives are, you can come back up here and you can do an implicit differentiation and kind of spark your brain on what it's going to look like. So from there, we're just going to go ahead and do some examples using those rules. I would suggest that you have those rules pretty handy, and they should be part of your flashcards as you're going forward so that you can go ahead and study them. So our derivative, f prime of x, 3 arc cosines of x plus 4. So that 3 is going to be 3 times that. It's a constant, so we can just go and leave that on the outside like we've done in the past. And we're going to take the derivative of the arc cosine of x plus 4. That is to tell us that we take the negative of the derivative of the angle, which is going to be negative 1, divided by the square root of 1 minus the angle squared. So we're going to take our x plus 4 and square it. From there, we can clean this up. If it's a multiple choice, you just got to play around with it. Really, what we're going to see is we're going to multiply the negative 1 and the 3 together, so we get negative 3 over the square root of 1 minus the square root of x plus 4 squared. Can we go ahead and rationalize this? We could. There's really not big a reason to it. It's pretty much going to be left in this form. Next equation, we have 2 arctangents of x squared over 3. So again, we're going to go ahead and take that 2. It's 2 times that. There's no variable with the 2, so we can leave the 2 on the outside. We're going to take the derivative of our angle. The derivative of x squared over 3 is 2x over 3. That's going to be divided by 1 plus the angle squared, which is going to be x to the 4th over 9. This one we're going to have to clean up. They're not going to leave it like this. They're going to make us clean up a little bit because we have fractions within fractions. You know I don't like that, and they're not going to like it either. So that 2, again, it's going to hang out there for a while. We can go ahead and find a common denominator for our denominator. So we have 2x thirds, or 2x over 3, divided by, common denominator is going to be 9. So we have 9 plus x to the 4th over 9. We can go ahead and multiply by the reciprocal. So our reciprocal there is going to be 9 over 9 plus x to the 4th. Our 3 and our 9 is going to simplify. So we end up with 2 times, we have 2x times 3, which gives us 6x. And that's going to be divided by the 9 plus x to the 4th. You might want to go ahead and clean that up as well. 2 times 6x gives us 12x divided by this here. We could write it as x to the 4th plus 9 or 9 plus x to the 4th. Really doesn't bother me either way. And that's our derivative of 2 arctangents of that angle. In our next example, we have x arc sine of x squared. Now we've got the multiplication. You knew we weren't going to get away from the product rule, didn't you? And we have a chain rule in here too. Oh my goodness. We just have a product rule. We'll get in chain rule a little later on. So f prime of x. We're going to have product rule, so we have x times derivative of the arc sine of x. So we have the derivative of x squared, which is 2x, and we're going to divide that by the square root of 1 minus the angle squared. So we have x to the 4th. To that we're going to add the arc sine of x squared times the derivative of x, which is going to be 1. From there, what we can do is really not a whole lot. We can multiply this x and 2x, I guess, together. So we get 2x squared over the square root of 1 minus x to the 4th. To that we can add the arc sine of x squared. We could find a common denominator. I don't necessarily know why we'd want to. We're pretty much just going to leave it like this and go on with life. If it's multiple choice, you should be able to do that manipulation and get to the correct answer. Our next derivative here, we're looking at the arc secant of 2x divided by 4x. This is kind of an interesting problem. We have quotient rule. We have two things being divided. We have x's in both of them. So we're going to have our 4x, derivative of the arc secant. We're going to take the derivative of the angle, which is 2, divided by the absolute value of the angle, times the square root of the angle squared, so 4x squared, minus our 1. Kind of looks a little weird, doesn't it? There we go. Minus our numerator, which is the arc secant of 2x. I'm going to put that in parentheses. Times 4, the derivative of our denominator. That kind of went away, didn't it? And that's all over the denominator squared. So we get 16x squared. Remember, we're going to square both the 4 and the x down there when we have multiplication. From here, it just becomes a clean up the problem. How can we clean this up? So we have a fraction within a fraction. They're probably going to go ahead and clean that up. We take our 4x and multiply it to the 2 and get 8x. That's going to be over the absolute value of 2x, square roots of 4x squared minus 1. From that, we're going to subtract 4 arc secants of 2x. And that's, again, over our 16x squared. I'm going to run out of room. Maybe I'm going to have to combine a few steps here. So what we can do, this absolute value of 2x, we should see that the absolute value of 2x can be written, or is equal to 2 times the absolute value of x, isn't it? So we could pull that 2 out, and that's going to be important because we're going to be able to cancel it with that 8. So that's going to give us a 4x over the absolute value of x squared to that. We can go ahead and find a common denominator. So I'm going to go ahead and do, since I'm running out of room. So we have our 4. This whole denominator is going to come up to this one, excluding that 2, because we've already divided it out of the 8. So we have the absolute value of x, square root of 4x squared minus 1. And then times our arc secant of 2x. Since now we can take our two denominators and bring them together. So we have 16x squared. Again, remember that 2 is gone. Became our 4. So we get the absolute value of x, square roots of 4x squared minus 1. The only other thing that I see that we could probably do, looks like we have a 4 in common with the numerator and the denominator. So that's going to go ahead and cancel out and give us a 4 in our denominator. And that's going to pretty much be what we're going to see. So again, it's kind of sloppy. Let me get a piece of paper here, rewrite that so it looks kind of nice. It would be x minus the absolute value of x, square roots of 4x squared minus 1, arc secants of the angle 2x, divided by 4x squared, absolute values of x, square roots of 4x squared minus 1. And that's going to pretty much be the way we're going to leave that answer. I got just one last one for you today. Here, f of x is going to equal the cosine of the arc sine of x. So here's our chain rule that I was talking about before. So a little teaser before. Now we're going to go ahead and untease it, I guess. So how do we find the cosine of an angle? Well, we know the derivative of the cosine of an angle. Derivative of cosine is negative sine of the angle, so the arc sine of x. Then we take the derivative of the angle. So the derivative of the arc sine of x, That's where we're going to go ahead and use our rules. So we talked about that already. We used implicit differentiation. I gave you the rules. Either way, doesn't matter to me. We're going to remember. And we get 1 over the square root of 1 minus x squared. The only thing that we are going to see to be able to clean this up, if I take the sine of the arc sine, so the sine of the arc sine of x, those are inverses of each other. So I'm going to end up with a negative x from that form, or from that angle, times 1 over the square root of 1 minus x squared. The only thing then you can clean up negative x times 1. Remember, that's over 1 if you need. So we get negative x over the square root of 1 minus x squared. And that, my friends, is going to be the derivatives of the arc sines, or the arc trig functions, or the inverse trig functions. Again, if you want, you can remember those rules, or come up here and do a little implicit differentiation to help you out to remember what those rules are. Good luck, enjoy. If you have questions, you know where I am. Good luck.